All right, let's get started. Let's first have a show of hands. How many people have used tracing in any form with Elixir? Okay, I don't know, maybe 10, 15. And how many use tracing on a regular basis? 1, 2, 3. Anybody in production? 1, 2, 3, 4. Okay, the courageous one. So my interest in tracing started about 10 years ago. I was working back then in Sun Microsystems, a software architect, and we built this highly scalable video streaming server with customized hardware and a distributed application written in C++ on top of it. And troubleshooting this complex system was extremely challenging. So there is this quote that I like that says, if you have a hammer, everything looks like a nail. And it was clear for me that the tool that the tool I was using wasn't the tool for the job. And so I started looking for better tools. And I didn't have to look very far because at Sun Microsystems about that time, Brian Cantrell developed a tool called dtrace, which allows you to inspect code from the kernel all the way up to user space. And when I made dtrace, it was like suddenly I got X-ray vision. I was able to see code running at any level of the stack. I was blown away. So the objective of this talk is not only to provide you with useful information, but also to inspire you about the possibilities that tracing can open up for you. So let's start with what exactly tracing is. So let's turn to Wikipedia. And the Wikipedia says something like that tracing involves a specialized use of logging, and then keeps going and says something like, well, there is not always a clear distinction between tracing and other forms of logging, which is, it shows that there's still a lot of confusion about logging out there, about tracing out there. So let's clarify this a little bit. So tracing is a technique for troubleshooting a running system by actively observing its internal operation with reduced interference. And I'm stressing out actively observing, because for me, logging is like a passive way of observation. When you're using logging, if you're not giving the logs that you need, you're pretty much out of luck. Opposed to that, with tracing, you can just go back and extract the information that you need from your running system. Also, I mean, if you use like other ways of debugging, like with a debugger, you put a breakpoint, that has like you're stopping the operation of your system, so you have like a big interference with how the system operates. So it's obviously that's different than tracing. So the tracing workflow basically calls for run a set of experiments in an iterative way. And the way this works is similar to how you play guessing a character. So when you play guessing a character, you don't start like throwing names right out of the bat. So what you do is you first like ask a question like, is this a male or a female? Is this like a celebrity? And what you're doing is using divide and conquer in order to narrow down the solution space, and you iterate through these questions over and over until the solution space is small enough that you can make an educated guess of what's going on. And with tracing is similar. So on one iteration, what you do is first you formulate a question. That's what you want to understand on your system. Then you create a tracing experiment. You run that experiment, you analyze the results, and make a conclusion, and you repeat over and over until hopefully you gain more information about your system. So let's switch gears and let's see how this works on Elixir. So Elixir runs on top of the the Erlang virtual machine, and with the Erlang virtual machine, you have the possibility of observing all bunch of events on your system. So for instance, you can look at process activity, when a process is spawned, when it's destroyed, when it's registering, register its name, when it goes in and out of the scheduler, when happen garbage collection, when you can look at when a particular message is generated, function calls, and there is this thing called sequential tracing, which allows you to tag a particular message and see how it propagates between processes, which is very powerful. But like when you embark in a new activity, it's important that you become aware of what are the dangers of that activity, and tracing is no different. So what is the worst thing that can happen with tracing? So the worst thing that can happen with tracing is you can pretty much crash the VM. And this is very different than the let it crash that you may have heard in the Erlang circles. Because when you crash a process, you have a supervisor that's taking care, it's going to restart your process, and everything is back to normal. Nobody has even noticed anything. But when you're crashing the VM, I mean, really, you're bringing your application down. And worse yet, you may be actually bringing the whole cluster down. So certainly, this is something that you want to avoid. Anecdotally, if you have read the book of Erlang programming, and I've gone through the exercises, then looks like one of the authors of the book, by careless use of tracing, they caused like a nationwide outage of a mobile network. So, certainly this is something to be very careful. So the way that many tools have addressed this is by, focusing maybe in development. And while that is useful, it kind of defeats the purpose because tracing is mostly useful. It's precisely useful whenever you have like a system in production, because we all know that bugs have this characteristic to show up at a very worst moment with the most important customer, and maybe it's like so hard to replicate that this is the only chance you have to figure out what's going on, right? So we're going to see ways how you can run this in production. So how tracing works in Elixir. So we'll look at an example. The first thing you need to do is need to figure out what you're interested in tracing. In this example, we're going to be looking at send messages for a particular process. And whenever you ask, you need to ask from the virtual machine that you're interested in that particular tracing. And when that tracing when that event happens, then the virtual machine is going to send your tracing process, here depicted in green, a message. Right? And this message is just like any regular message, but it looks like a tuple. And the first element is going to have the atom trace. The second element is going to have the process ID of the process that is being traced. And then the third one is going to be the type of the tracing. In this case, is the send atom. And there are going to be other parameters that are going to differ depending on the kind of tracing that you're doing. So depending on the tracing types that you're doing, you're going to have like a very different message can be sent to you. And for instance, if you're doing send, receive, or tracing calls or procs, the beginning of the tuple are going to look the same, but depending on that, you have different parameters. Okay. Now, in order to enable tracing, Erlang provides us with a built-in function called trace, which receives 3 parameters. The first parameter is a PID spec, and the PID spec is either like a process ID or could be a keyword which represents all the processes on the system, or could be just the new processes or the existing processes. The second parameter is going to be a Boolean that's going to tell the virtual machine if you want to start tracing or stop tracing for those particular processes. Then the third parameter, you're going to have like a list of flags. And this is where it gets interesting, because there are like a gazillion flags from many different things that you can combine and mix and match. So these trace flags are the main categories are followed. First, you have the trace types, which we have seen. You have procs, send, receive, garbage collection, and you can combine them as well. The second parameter is like inheritance. And basically what this allows you to do is whenever a process that is being traced creates another process, then it can choose to propagate its tracing flags to the first generation of processes, or maybe to all its descendants. And this is very powerful. We'll see an example where this is useful. And last, we have like generic tracing modifiers, like add a timestamp to the tuple, or use an arity instead of using passing all the parameters. And there are more modifiers. Now, if you're doing function tracing, enable tracing like with the previous command is not enough, because you also need to specify which function you're interested in tracing. And before that, you're not going to get any trace. And this function is called a trace pattern and has also 3 parameters. The first one is an MFA, which is module function and arity, which is a way that you identify a function in Elixir. The second parameter is it could be true or false. So to specify if you want to enable tracing on functional tracing on that particular function or disabled, but also accepts a match spec. And a match spec is a way that you match for particular arguments. And we'll see that later. And the third parameter are yet more flags, which could be either global in case that the function is being called with a fully qualifier notation in which you have like a module dot function, or basically you can have a local in which like you're going to cover all the function calls. But one important thing to notice here is that call tracing, these particular functions are going to apply to all the processes for which you are doing call tracing. So you cannot just kind of like set this thing for a particular process only. So match spec is a way that you specify a particular form for the arguments, and this is similar to the way you do pattern matching with a case statement or with a function clause. So basically, it has three parts. First, it has the head, the condition, and the head you specify like what are the parameters that you have. In the condition, you have like here when is list with one of the parameters. And then when these two match, then basically you execute an action. And basically you have many options for actions here. Like for example, you could send a message to the process. You can enable or disable tracing, particular set of tracing, and there are like many other interesting actions that you can do. But what is interesting here is that in order to specify this, you need to use a particular notation, the one in the second line over here. Which has this $1 for the unbound variables. You have like more than one. You have $2 and so on, and it's very complex and cumbersome. And we'll see how we can other ways later that we can use. Now this is a tracing example, like a simple one in which like we want to trace, do function tracing as we already seen. You need to specify two functions. First, you need to enable call tracing for the process, right? You specify the process. And then that's not enough. You also need to specify which function you're interested in tracing. And in this example, we're doing underscore, which pretty much covers all functions. And when you enable this, basically, the virtual machine is going to send you like all the messages to your process, which is kind of like the terminal. And when you do flash, you're going to get bombarded with like an avalanche of messages, which may actually even like block your CLI terminal. So don't do that. But fortunately, there are like you don't have to deal with these low-level commands. There are like people develop many tracing tools on top of these two commands, and they provide you with a few advantages. First, they are the commands are more friendly. They also provide some safeguards so that you don't have the problem like the author of the book. And also they have like there are a few tools that provide a graphical user interface. Now this is like a table with the main tools available. It's not exhaustive. There are probably more tools out there, but these are the main ones. And they're divided in three groups. The first group is the ones that have a graphical user interface that's on the left. Then in the middle, we have CLI-based tools. And on the right, we have tools that are based on kernel tracers. Okay? And one thing to note here is that the group in the middle, they are divided in two groups. First, you have the original Erlang tools, and for which like a few have wrappers for the original Erlang tools, Elixir wrappers that provide you with a way to make the commands using the Erlang syntax. We're more friendly and then easier to integrate with Mix and so on. But fundamentally, they are the same tool, so they don't add any functionality on top of the original tool. Another thing to note here is that you have in red which ones are not safe to use in production because there is no safeguards and you can leave things running. And then there are others that are experimental, otherwise in green are safe. So we're not going to go through all the tools, but we're going to just pick a few so you get a gist. The first one we're going to talk about is DBG. It comes with a runtime Erlang distribution. So it's provided by the Erlang core team. And what they try to solve here, what we try to do with this tool is to make tracing session in CLI most efficient. And the way they did that is by, before you can combine all these flags, and which was very difficult, long to type on the CLI screen, terminal. And so they did is like, what they did is like they make all the combinations, right? And then they created commands for each combination. So now, before you have 2 commands, but now you have 60 commands. And like these commands have like these cryptic names, acronyms like CTP and something that stands for something, which they're difficult to remember. But they provide other features, like they manage a tracer process for you. And one important thing is that they have a function called fan2ms, which allows you to specify match specs in functional format, which is actually very important. And most of the other tools use this function because it's an easier way to specify match specs. The second tool we're going to briefly talk about is ReconTrace, and there is the wrapper ReconEx. And Recon focuses on call tracing, so they don't cover all the other forms of tracing. But the important thing they provide is a safety. And they do that by requiring you to specify a parameter in which you said, what is the maximum number of events that you want to receive? In this example, 100. And after you receive these 100 events, then tracing is going to finish, and there's not going to be more tracing. Another way, instead of that, you can specify also like event rate. So in this case, like 100 calls per second. And then, so basically, you have a safeguard when you're in a production system that you can feel more comfortable. The next tool, it's a graphical tool called EarlyBurly. And EarlyBurly is actually a Java application which joins a cluster and is able to kind of like instrument a Erlang or Elixir application. And EarlyBurly is intended for development. So they have like a few features that are useful for development. Like for instance, if you go and reload your module, like what happened in Phoenix all the time when you're developing, then basically EarlyBurly is going to reapply all the trace commands for you, so you don't have to go and do that again. And the way it works is that once you connect, you're going to see that there is a pane with all the modules, another pane with all the processes, and you can click on this in order to enable tracing. And you're going to get all the tracing events into another window, and you can just go and filter or search. So basically, when you have all the information there, they provide you with ways in order to try to look for the information you're looking for. And it's, as I said before, it's not safe for production. Last, they have this group of kernel tracers, and these are very powerful. Depending on which OS you are using, then you may have one option or two to use. You can use only a few of these tools. So for instance, if you're using Linux, then you can only use SystemTap or LTTNG. If you have Solaris or Mac, then you can use dtrace. And I'm not sure, there is an option for Windows. But so basically, the way this works, at least for SystemTap and dtrace, is that you need to recompile your Erlang distribution with a particular flag. And once you have this new distribution, it's kind of like a experimental kind of like build. And then basically all the instrumentation is enabled, and you can run your commands. But dtrace and SystemTap, they're still very limited in the way that there are a lot of things that are not provided. For instance, you cannot do stack tracing. You cannot do, whenever you do like call tracing, you don't get the parameters. I just get like the function calls. And so the integration is not full integration into these tools. So hopefully that's going to keep evolving in the future. Now for LTTNG, the Erlang core team, they took a totally different approach. What they do is they use LTTNG as a back end for Erlang tracing. And what it means is that you will use the same Erlang tracing commands that we have seen in order to enable tracing, but instead of sending them to your process, what's going to happen is that all these events are going to be sent to the LTT backend, which it's very efficient, way more than handling the process, the events in the process yourself, but also have it's much more safe. And this is available as in an OTP 19. So there are many problems for which tracing is a perfect fit. And the truth of the matter is that the adoption of tracing is very limited. We have seen here that almost nobody really uses tracing. So, even though we have all these tools, certainly we're still facing challenges, right? So let's go over some of these challenges. The first problem we have is that you may know exactly what you're looking for in the system, what you want to find, but it's very hard to translate this question that you have in your mind to an actual tracing command. So, the gap is very, very far. The tracing command it's very low level. The second problem is that when you enable tracing, most often you get like an avalanche of data, like a ton of data, and it's almost like you're looking at the metrics when you're not the one. All you see are squiggles, right? And basically there's still a gap between taking this amount of information and converting that into amount of data and convert that into information or even knowledge, to be able to keep making experiments and learning more about your system. And last but not least, it's very difficult to enhance these tools and to collaborate. So at this point, you might be thinking, wouldn't it be great if we have like a tool that you just like throw your question at the tool, and the tool will just go and automatically go and create the tracing commands, run the commands for you, and it will just go and collect all the information and basically provide you with the answer. So now there is Enter Tracer. So Tracer is a new tracing framework for Elixir that first operates with a high level of abstraction. So you can just deal with high-level questions that are easily to articulate. Second thing is it can be extended by the community, and also is safe to use in production. So Tracer has this concept of tools. And tools are basically components that address a particular problem space. So they are built on top of the Tracer framework, so they use all the primitives and services. And let's say, for instance, that you're interested in how many events of some kind are happening. Then you will use the count tool. If you want to know how long things take, you're going to use the duration tool. And if you want to have a more insight about what's running in the system, then you can use the flame graph tool, and so on. So let's see how this works. So first, the first thing you need to do is to choose what kind of tool you want to use. And once you do that, you will configure your tool, and you provide the parameters, the question that you want to execute. And the tool is going to go and it's going to create a probe, like a set of probes. And each probe is a representation for particular tracing commands. So you're going to have probes for call tracing, probes for prop tracing, and so on. And it's going to go and collect all and create all this information on behalf of you. So this is kind of conceptually similar to how Ecto works. Because with Ecto, when you go and assemble an Ecto query, and you may do that in steps and assemble your query, but nothing really is happening until you take that Ecto query and you apply that to a repo. So similarly here, whenever you go and start configuring a tool, which is on behalf of you doing all these probes, nothing really is happening. There is no tracing going on. So tracing will only happen whenever you run the tool, okay? So when you run the tool, basically Tracer is going to take that tool, and it's going to inject a process into the tracer, into the node that you want to trace. And at the same time, it's going to create a tracer process that's going to collect all the information. So it's worth noting that when you're doing this kind of tracing, you don't have to embed this tool inside your application. So you can just have an application that was written a long time ago, which is running somewhere else. As long as it can run as a cluster, you can just go and inject this simple process there. And once tracing starts and you start collecting all the tracing events, eventually you keep, the tracing process is going to, the tracing tool process is going to collect all the information, and at some point it's going to provide the result to the client or as a message, or it's going to print that to the terminal. And when everything ends, Tracer is going to restore the system to its original state. And this is important to note, because you won't be able to have a situation in which you forget tracing enabled, and suddenly everything's slowing down in your production system. So what are the failsafe mechanisms that we have in Tracer? So the first thing is that Tracer, a tool, will run for a maximum amount of time of, the default is 30 seconds. You can customize that, of course. Also, the maximum number of messages, similar to Recon, it's 1,000, it's a default. And on top of that, the tracing framework is going to observe the size of the message queue, and if it detects an overload, because there is a lot of messages queue in the message queue, then it's going to abort the tracing and everything goes back to normal. Now, tracing can be installed as an XPM package, so you can add it into your project. And this may be useful if you want to do some deep integration, or maybe you can use it for your tests. If you have like a you want to identify an event that needs to happen in your system, and instead of doing like a complex mock, all you need to do is basically include the package, and then look for that particular event, and you can use in your test. But most often than not, you're going to be using a tracer in IEX in a remote session, so you can inspect another node. So at this point, I mean, if you're interested in following up with some of the examples, you may want to download the package and follow along. So in order to run IEX, what you need to do first, you clone the repo, then you get the dependencies, and then you fire IEX, and you provide a node name so that you can join a cluster. And then you use the use tracer directive in order to be able to use tracer commands directly without the tracer prefix, which is simpler. And then once you do that, you can run a tool, like with the run command. The first parameter is going to be the name of the tool, which is just a module. And people, the intention is that people to create their own modules, their own tools. And the second parameter here, it can be optionally a node name if you want to trace a remote node. So let's first go over a count tool as an example. So with the count tool, what you want to do is count events. And the first parameter you will pass to the count tool is the process that you're interested in tracing. In this case, is the self process, and which is actually the default, so you don't have to enter that option in this case. And the next parameter is going to be match. So with match, you're telling what exactly you want to count. And you need to specify if this is a global or local. We have seen that before. And then you specify a function with a set of parameters. And in this case, we're going to be counting the number of calls to string split. And we have two parameters, string and pattern, which is they're both unbounded parameters. And when you run this thing, and we execute, let's say, 4 calls to string split, and you finish tracing after it collects everything, what you get is a table. And in that table, in this example, you see that you get all the options for the unbounded variables that match. And for example, in the case that you have string hello world and the pattern space, you see that this has been identified that were called 2 times, and you see the number 2 there. But let's say that now you want to dig further, and you want to know how many instances of call we have whenever only the pattern was the letter O. So you're binding the O to the second parameter, and what happens now is that with that binding, now a lot of the calls that we made before, they're not going to match. So they're not going to be part of the result. And more than that, whenever we get the name of the unbound parameters arguments, we're not going to see there that the second parameter shows up. And then if you go and change the first parameter to an underscore, that means that you don't care about the first parameter. And then the result is that now the 2 different calls, the hello with the O and the hello world with the O, they are going to be aggregated into the single count. So now you have a 2, and there was nothing really to, there was no unbound variable there to show. Okay, and this is a very simple example, but I'll give you a sense of what are the things you can do. Let's look at a more useful example. Okay, let's say that you have a Phoenix application, and you want to know how exactly the REST calls are, what kind of REST calls are hitting your Phoenix server. Okay, so what you will do here? The first thing you will do is you need to consider, okay, first, which process I want to trace. And this is tricky because if you know how Phoenix works, the process that is really handling your controller doesn't exist by the time we're making this tracing call, we're setting this experiment. Because only by the time that you're getting the actual REST call, there's going to be a new process that's going to be created, and in that process, everything's going to be running. So the process we want to trace doesn't exist yet. So the way we do this here is that we provide the name of the supervisor. In this case, is the endpoint, the fancy app endpoint. And the tool is smart enough. It say like, oh, OK, this is a supervisor. Well, you probably intend to trace all the descendants, and not only the descendants, but also the processes that are going to be created by the descendants. OK. The next thing here to consider is that what kind of match function you want to match. And in this example, what we're going to match is to the router call. And the router is like a plug in a way. So the first parameter is going to be a plug connection structure. And a few of the parameters on the connection structure are interesting. In this case, we're going to look at the method and the path info, which describe like what is the URL in a way of the call. And when you run this thing, what you get is like a table where you see what were the REST calls that were made to your system. So in this case, you got 45 calls with the method get and the path user and a particular user ID. Okay, so you can see now that just by modifying a few of the parameters, you have like a lot of control of what to observe in the system without having to deal with low-level commands. Now let's look at the duration tool. With the duration tool, pretty much you are going to be measuring how long a function takes. And the parameters here are similar to the ones before. For the sake of this example, we're going to look, instead of looking at the router, we're going to look at the user controller, at the index method. And in this example, whenever like we start getting this command, this REST command invocations, then we're going to be measuring how long it takes to execute that particular function. And in this example, we can see right off the bat that there is one call that it took like about 8 milliseconds, while the other calls were like much faster. So maybe you want to go and dig further there. But if you're running this in production, you may get like 1,000 requests per second, and you're going to have like tons of lines there. So you may want to just get a sense of what is the worst case scenario, or what is the maximum duration that you have. And for that, you have aggregations. So you can specify if you want the minimum, maximum, mean, or whatever aggregation over all the different results that you got. And in this case, we know that the maximum, so we choose the aggregation max, and the maximum is going to be the 8 milliseconds call that we saw before. And right now, we know what is the maximum, but you don't get a good sense of it was only one or there were many. And so certainly, you make your output more concise, but you don't have like a good sense of what's going on in your system. So what you need really is the distribution aggregation. And with the distribution aggregation, the way it works is that all the results are going to be bucket into a logarithmic scale kind of like metrics. And like for example here, we have that you have 10 calls that for which the duration was between 128 microseconds to 256 microseconds, while you only have one call that was between 8 milliseconds to 16 milliseconds. So the advantage here is that just by getting a simple, result, you can get you can get a sense of what's going on in your system very easily. So the next tool we're going to talk is like a call sequence tool, and the call sequence tool allows you to figure out what are the functions, what are the call sequence that you're going to have when you hit a particular function. So basically, it's how a function it's not only implemented, but a particular call trace that for the parameters that you are using are going to be executed. In this example, we want to know, for example, the map.drop function. Is that, let's say, we want to know if it's calling directly like an Erlang function or what's going on inside. And in order to do that, we have like a lot of parameters that you can use. By default, that's not going to show any argument, but you can enable to show the arguments or the return values. And the way this works, it's a little bit different. It's like instead of like focusing on a particular function, we're going to enable call tracing for all the functions. We're going to receive all the call tracing events. And then once we get the one that we want to trigger, then we're going to start collecting the information. So we're going to get much more events than before. So we need to bump up the maximum message count and the maximum queue size, because otherwise this experiment is going to finish very early. And this is the result of that particular one. So you can see what is interesting here is that you see the different calls are indented in a way that you can see exactly which calls are made at the same level and when like you have a call that is returning and you have all the parameters there. So it's much easier to figure out what's going on and only you see what you want. The last tool we're going to talk about is a frame graph tool. And before we talk about the tool itself, let's just look at what frame graphs are. And frame graphs are like a very interesting topic. They serve like a talk by themselves. And what they are is it's just a visualization that allows you to easily understand frequent code paths. So basically, you can see they're all like different stacks that are being aggregated. And every horizontal line represents a particular stack frame. And doesn't mean that even if it's like continuous, doesn't mean that that function has been called only once, but all the calls have been aggregated. And if you may be calling a function many, many times, and they were very short, but when you aggregate everything, basically you're using a lot of your CPU. Okay? And this is very useful to understand what's going on in the system. So the frame graph tool is very simple to use. All you need to do is provide a file name where you want the SVG. It's like an SVG file that is resolved. And if you don't enter that, you're going to get the default name anyways. So in our example, what we're going to do is we're going to run this trace, and then we're going to go and issue like a REST command to our Phoenix server, and then we're going to stop the trace. And the result that you get is like this frame graph. And in this frame graph, if we look at it, basically what we see, there are like two PIDs which are in the bottom, two processes. The short process is like the cowboy supervisor, and the second process on the right is the Phoenix code reloader, because this is like a development Phoenix application. But we don't see a REST call. And at the top, we see that after they do their thing, they're going to sleep. So this is not very interesting. And the thing here is that the REST call created a process and execute so quickly, and it went away, which is insignificant here. So you don't see anything. So what we do is we dig deeper, and we do that by providing additional parameters. First thing, we don't want to see those sleeping, the previous processes that are sleeping. So we're gonna use a parameter called ignore sleep, and so those are not going to be shown. And then we are going to increase the resolution from 1,000 microseconds to 10 microseconds. So now you have more resolution, and also increase the max depth of the trace. And once you do that and you rerun, then you get something like this. And this is way more interesting. And one nice thing about flame graphs is that they're interactive, so you can just click on different places, and then you can zoom in and see what happened there. So this is not like so it's important to note here that this is not like a time diagram. So basically, you are collecting all the information for during that period of time. Now, we were interested of maybe looking at our user controller, and our user controller actually is the bar that goes farther up in this diagram. And if you click on that one of these frames, you get basically a zoom in of what's going on there. So you can see that you have here like the user controller index call, and then eventually you also have the rendering of their views and all the different calls that are happening there and so on, and which is interesting. But the way that really this is useful, I mean, this is like a simple example. If you have like a database call and many other things, then basically you will see very different patterns and learn a lot about your system. Last, very quickly, we're going to go about tool structure. The whole intention is here is people to create tools that will be beneficial for other people and do very specific things. And in order to create a tool, it is very similar to the structure, very similar to a gen server. So you have a initialization function. First, you need to include the behavior, use tracer.tool. And then you're going to have functions for handle start, handle when the run start, handle event when like a tracing event is received, and then you're going to collect all the state. And at the end, when the run finish, you're going to have like a handle stop, and that's when maybe you want going to go and generate the output. And last, this is like an example of the initialization of the counter tool, a little bit simplified. And we can just see here that the first command is like init tool, where you're initializing the tool, and you're also processing whatever parameters that you want to handle in your tool. In this case, the match specification. And once you get a particular one, in this example, what we're doing is we're getting the process that the user specify, and then we're requesting all the children, and that's what we're going to be creating using for the probe. So we're creating here 2 probes. The first probe is going to be for the call tracing, and the second one is going to be for set on spawn. And for the call tracing, we're going to pass along the match specification, which is the function that we provided before, and basically, it's not doing really anything to that, because the whole match thing is handled with meta programming, so we don't really need to do any processing here in the tool. And then we set those probes, and when the tool is run, then basically everything will be taken care. And so just to recap, so we have productivity, and we also address extensibility and safety, and this is Tracer. Thank you.
We have time for a couple of questions.
Thank you very much. Is the Tracer tool module just a wrapper around GenServer, or what's actually there?
Can you repeat that?
In the tracer.tool module that you were using to show the tool that you were building in the second to last slide, is that just a wrapper around GenServer, or what? How do you actually implement that?
There is a GenServer that manages that stuff, but it's not a wrapper. Basically, it's making a call, so it's kind of like the other way around. And this is still like a little bit preliminary. It's a brand new thing. This interface may change a little bit, but the idea here is that you don't want to deal with like a lot of the complexity. So a lot of stuff is hidden from you. So there is really like a process that is handling everything for you, and it's only making a call to your module whenever something that it's the module need to perform happens.
I was curious if matchers that don't match have any cost. Like if you start setting up like hundreds of matchers that are only going to match like once a day in your production application, is that going to be dangerous?
That's a very good question, and I don't have actual. I don't know for certain, but my feeling is that first of all, the more you're tracing, you're going to have more overhead on the system. Okay. But I think that most of the overhead that happens really is from the message passing. So if you actually have all these matchers, but they don't match at all, then the overhead is going to be minimal. Obviously, there's going to be some overhead. I mean, to have zero overhead is when you're not tracing. So when you enable tracing, the virtual machine needs to go and start like before they issue a function or they generate create a process. Then they need to look and match against these things. So there are some instructions that were not done before, and now they need to execute it. So there is going to be a little bit of overhead, but my feeling is it's not a lot. The real problem is when you get this avalanche of messages, and you bring down the system, mainly because the message queues start to pile up, and you run out of memory. So that's the real problem. So if that doesn't happen, it's not a real problem.
Okay, we have time for one more.
I was just curious if you could go into what exactly is going on when you run the tracer tool and it starts a process on your remote node, the tracer process.
Yeah, so that's actually an interesting question. So basically, what happens there is that I mean, you basically the first thing will happen is you will join the cluster, okay? So you were in a separate node, and you have a node that has nothing to do with tracer, and you specify, what is the node name. You're going to join that cluster, and then basically you're going to inject. You're going to create. You're going to send the code actually to that node. You're going to recompile, because you may be using a different Erlang distribution. So you're basically sending your code there, and you're executing. You're creating a new process there, right? So one thing to note here is that Tracer has no dependency on other libraries whatsoever, and what you're injecting into your node that you're tracing is very minimal, right? So because obviously we don't want actually to come with a lot of baggage and things, and people may be concerned about, you're running your system. You don't want to actually start like adding a lot of stuff there. So basically you are injecting the code, a process, and you're launching that, and that's going to be sending the information back to your node, to your tracing, to Tracer. And once you're done, that process is going to be killed. So nothing is going to be running on your tracing node.
Okay, so do we have one more, or that's it? Okay, one more.
So this is ElixirConf, and we're talking about the exciting stuff on the Erlang VM for it, but what's the cost-benefit analysis that you see for something like a open tracing, thing like that instead?
So how this relates to
a distributed
Elixir?
tracing system that's not specific to the Erlang VM for performance or use instead of the specific Erlang stuff?
So I'm not sure I understand the question, but basically, when you're running Elixir code, you're running on top of the Erlang VM, right? And then so we're leveraging that, those capabilities from the Erlang VM in order to do tracing. Now you can do tracing outside, like with the OS tracing tools, the kernel tracing tools. And in order for that to be useful, really, you need to rely on the instrumentation that you have within the Erlang machine. And the problem there is that by default, none of those are enabled. So you need to go and recompile that and have a brand new distribution which has been fully instrumented, and obviously it's much more costly.
So the cost of adding that instrumentation is the drawback?
Well, not only that, and I think that the main issue is that whenever you recompile the Erlang virtual machine with additional code that are not used by most of the people and not used in production, then it becomes a little bit more concerning if you want to use that in your own production system, because it has not been tested as thoroughly enough like the standard Erlang distribution.
Okay.
Right, thank you.
Thank you so much.